Page 364, lesson 6.1 is on solving systems of equations by graphing. We're going to talk about this a little bit here, but then we're going to go to the concept bite on page 370. So a system of equations is when we have at least two equations, at least two linear equations. We have a system of linear equations. And when we have a system of linear equations, we're going to try to find the solution or solutions for that system of equations. The solution or solutions would be any ordered pair that makes all the equations in a system true. So basically, what we're looking at, if we're graphing our lines, the solution for the system of equations is going to be where the lines intersect each other. So like you can see this on problem 1, they graphed the two lines, they met at the point 2, 4. The reason we're going to look at this concept bite, which actually shows us how to do this on our calculators, is that we're going to be learning different methods to solve system of equations, working them problems out by hand that are going to be quicker and more accurate than by drawing the graphs and finding the intersection. The reason I say that is if you graph this out, you find your points, you graph the line. One thing is your lines may not be perfectly straight. If your lines are not perfectly straight, you're not going to get the exact solution that you need. The other problem is that the solution doesn't always come out evenly. So like on this problem, the solution was 2, 4. Well, that's great. But, what if my line, I'm going to draw a black line off to the left here. What if this was my line? Okay, you might say, well, it looks like negative 1.5 and 1/2. It might be, but it might not be. And even at that, there's other possibilities where, you could get something that's just right in between. And, it could be that it's got like 5 1/7 or something like that. So that's the other reason. Besides our lines may not be exactly perfect, the other thing is the answers may not always be perfect. So we're going to look at, with the concept bite, how we can do this on the calculator, on the graphing calculator, if you're allowed to use those. And if you're not allowed to use those, we'll learn in other sections how we can work that out by hand. Page 370, looking at the concept bite. This is going to show us how we can work these problems out on our calculators, which is the only time we're going to do the problems this way, like I mentioned. So if you look down at the activity, we're going to skip over that top part. In the activity, they want us to solve this system using a graph. So you can go ahead and start working through this on your calculators. So if you have any lines in your calculator right now, any equations in there, you can clear those out. And then y1, you can put the negative 5x plus 6. And then the y2, you can put the y equals negative x minus 2. When you do the negative x minus 2, make sure you're using the negative button in front of the x. You cannot use the subtraction button, or it'll give you a syntax error message. And then after you do that, you can graph those. Ideally, if we're lucky, we're going to see the intersection of the lines on the window as it is. If you don't see the intersection of the lines, you may have to adjust your window, and we'll talk about that more later. We can deal with that as we come across that issue. Once you've graphed those, then we're going to use the calc feature. So along the top part there, if you're not seeing the graph, a possibility also, since we just did some stuff with scatter plots, you may have to change your window there. If you do zoom 6, Zoom 6 will get you back to a standard window, which is -10 to 10 on your X, -10 to 10 on the Y. And then the calc, that's second. And then one of the top buttons on your calculator is the trace button. Second and trace, the secondary feature of that button is the calc, which is calculate. So we're going to do calc and we're going to do intersect to find the point where the lines intersect. One other thing you may have to consider is we just had somebody got an invalid dimension code, and the issue was plot 1 was still highlighted. So if plot 1 is highlighted, you might have to go up to that on your Y equals screen, arrow up to plot 1, hit enter to unselect or deselect the plot 1. Once you've chosen intersect, it's going to say first curve. You're going to make sure the cursor is close to where the lines intersect, which is where it should be. Hit enter, it'll say second curve. Again, make sure it's close to where the lines intersect, hit enter. And then very reassuringly, it will say guess, question mark. And anyway, the calculator knows what it's doing, so no worries. It's not just guessing what's happening here. It will find the correct intersection point of those lines. So that intersection point should be 2, -4, if you've done that correctly. So going back to page 365, we're going to look at problem 2. And we're going to be doing this, though, with the idea that we can use our graphing calculators. More accurate method. And like I said, we'll learn how to work these out by hand if we can't use a calculator. And it's going to be an accurate way of getting a good answer, no matter if it's a good, nice, even number or not. So problem 2, we're looking at the weights of these two alligators. They have initial weights and their growth rates. And then it says after how many months did they weigh the same amount. So what we're going to do, we're going to be graphing lines for what the weight of each of these are. And you can see the one started out, it didn't weigh as much, but it's growing at a faster rate. Its weight is increasing faster than the other one. So eventually it's going to catch up to and then pass up the weight of alligator 2. So they came up with these equations. They defined their variables. Again, we should probably say let W represent the alligator weight, and we should probably say that's in pounds. And then let T represent the time in months. Okay, so these could be our equations. So they just did the starting weight plus how much it grows times however many months for both of those. When we do these, if we were doing these in our calculator, obviously we're not going to be putting W's and T's. We're going to be putting Y's and X's. So this would be like Y equals 4 plus 1.5X, and this would be Y equals 6 plus 1T, or just 6 plus T. And then we can do the same thing that we did a minute ago on the concept byte. We can graph those, we can find the intersection point. The intersection happens to be pretty nice here, and that's fine. But like I said, we're going to learn a way later. We can do it by hand, and we'll pretty quickly get the same answer either way. So anyway, when you go, if you would go to graph those on your calculator, find the intersection, you should find the intersection point to be 410. If you didn't get through all that yet and you want to go back and look at it later, you can. We're going to move on to the got it, and we're going to do the same thing, working through this on our calculators to find the intersection. So for the one satellite radio service, it's $10 a month plus this $20 activation fee. Activation fee is just a one-time cost. Okay, so this would be like Y equals 10X plus 20. If X would be our number of months, and Y is our total costs. Okay, we'll want to define those a little bit nicer maybe than what I'm doing here quickly. But then our second service, it's $11 a month plus activation fee of $15. So that equation would be y equals 11x plus 15. And then at this point, we are going to graph these on our calculator. We're going to let the calculator guess what that intersection point is. And we're going to figure out our answer here. So if you work this on your calculator, you find the intersection point. The intersection point should be 570. And then we need to make sure we're answering the question. The question was, in what month was the cost of the service the same? So if we interpret that to answer their question, we could say in the 5th month, the costs will be the same. We could be more specific and say it would both be $70. And then what we could do also with this, we could think about, you know, what if we did less than 5 months, what would be the better deal? And what if we did more than 5 months, what would be the better deal? So if we had less than 5 months, the one with the lower initial value or the lower activation fee would be a better deal. So if we had less than 5 months, this would be the better option. If we had more than 5 months, then this one would be the better option. It's got a higher activation fee, but it's costing less per month. So eventually it's going to become cheaper. But with 5 months, it's the same either way, whichever option we pick. Bottom of page 365 talks about different names we can give these systems of equations. If we have at least one solution, which is everything we've talked about so far, everything's just had one solution so far, but anyway, if you have at least one solution, it's called consistent. And a consistent system can be either independent or dependent. So if it's independent, it has exactly one solution. So all the problems we've been talking so far are consistent and they are independent. If we have infinitely many solutions, then they are dependent. And it would have infinitely many solutions if the lines are exactly the same as each other. And then if there's no solution, if the lines never intersect, that's called inconsistent. And if it's inconsistent, if there's no solution, the only way that could happen is if our lines are parallel to each other. Okay, so just a little vocabulary for our systems of equations. If you look at problem 3, they're asking for the solutions of these systems, and it says use a graph. So on problem 3, part A, I mentioned really we're going to do these problems if we're allowed to use a calculator. In order to use a calculator, you have to have y equals something. This first equation is not y equals something, so we'd have to get it to y equals first. We'd have to get it into that slope-intercept form. So first you can add x on both sides, and then you could divide everything by 2, and then that could be your equation. So that would be y equals 1/2 x plus 1, or y equals x over 2 plus 1 if you want. Now, interesting thing at that point you might notice is that our second equation is y equals 1/2 x plus 1. So it's kind of like in a code to start out with, where you don't necessarily see that they're the same. And then it's kind of like we transform this equation into that slope-intercept form, and now we can see, oh, they're really the same lines as each other. So really, once you've done that, I mean, you could use your calculator if you wanted to, but the solution, since the lines are going to be the same, they're always going to be intersecting each other. And so that means we have infinitely many solutions. So it's infinitely many solutions. You can see the graph off to the right there. And if they asked us to name it, we would say consistent and dependent. Dependent because it has infinite number of solutions. Part B is already both in slope-intercept form. In this one, if you're observant, you might notice that the slopes are both the same, but the y-intercepts are different. So if they have the same slopes but different y-intercepts, they're going to be parallel. They're going to be parallel lines. There's no solution then, okay? And you can see the lines over here. So no solution for this one, and that means that it is inconsistent. If there's no solution, it's inconsistent. So let's look at the got it 3. So for part A, if you want, you can put 1s in front of these. You could go to graph them on your calculator, but before you do that, you might notice that the slopes are the same. They have different y-intercepts, which means they're going to be parallel. Since they're parallel, we're going to have no solution. And to give a more description on that, if you wanted to, you could also say it's inconsistent. Okay, no solution is our main answer, but then we could also say that's inconsistent. Part B. So on part B, the second equation is not solved for y. We can get there pretty quickly though. If we divide everything by 3, we've got y equals 3x minus 3. And look at that. Our other equation is y equals 3x minus 3. So that tells us these lines are the same, which means we have infinitely many solutions. And we could also say it is consistent and dependent. So the concept summary just recaps what we've talked about. In a lot of situations when we're doing these problems for solving a system of equations, we're going to have one solution. We're going to have one point where the lines intersect. Okay, that means we have one solution. It's possible, like we talked about, the lines could be the same as each other, and then they would be infinitely many solutions. Or if the lines are parallel, then we have no solution. And remember, no solution is inconsistent. Infinitely many solution is consistent and dependent. And if we have one solution, then it is consistent and independent. So if we look at the lesson check number 5, we have some concert tickets here. So it's different options if we pay online or not. So it's $10 each online, but you have a service fee of $8 per order. And the other option is $12 each if you buy them at the door. And then presumably then no service charge. Okay, so it's kind of the risk here of, you know, maybe trying to get your tickets right away that you get better seats, and also make sure you get seats, that it doesn't sell out. Or I guess if you go that night, hopefully that they didn't sell out already, and then potentially it might be a cheaper option for you depending how many tickets you're getting. So first of all, they want us to write a system of equations, and they're telling us what variables to use. They're telling us to use C for the total cost and T for the number of tickets. And then we're going to graph these and find the intersection. So for the equations we are writing here, we're going to use C and T, but obviously if we do this on our calculators, we're going to be using Y and X. So our first equation if we're buying them online ahead of time. It's $10 per ticket plus $8 service charge. So C equals 10, T plus 8. This would be if we're buying them online. Our second equation is just $12 per ticket, so it would be C equals 12T, and that's if we're buying these at the door. So once we've got those equations, we can graph those on the calculator. So this would be like y equals 10x plus 8. This would be like y equals 12x. Notice they do have different slopes from each other, and they're not the same equation, obviously, then. So we are going to have one solution here. So the intersection point, if you work that out, would be 448. And this is actually going with part B. It's saying what is the intersection point and what does it represent. So for part B, we could say the intersection point is 448, which represents if you get 4 tickets, it costs $48 either way. Okay, and then we could analyze again on, you know, if you bought actually less than 4 tickets, at the door would be better. If you bought less than 4 tickets. And here's a way to think about it if you're not sure on that. And I know that's not asking you this question, but just think about if you bought one ticket at the door would be $12. And if you bought one ticket online, that would be $18. So that service charge is making it cost more initially. Once you get past 4 tickets, what's happening is it's kind of like we're splitting up that service charge between how many tickets we're getting. And so the more we split up that service charge, then it makes it to be where it's less than $12 a ticket if we get past 4 tickets. If you look at number 6, they want us to match the type of system with the number of solutions it has. So for 6, part A is inconsistent. And that would be no solution. If we have no solution, it's inconsistent. Consistent and dependent, that would be infinitely many solutions. And then that leaves us consistent and independent is exactly 1. I guess that's a way to think of independent. If there's just one, then it's independent. Okay? Kind of like if you're the only person, then you're independent of deciding on what you're doing or whatever. Let's look at number 8. Can a system of 2 linear equations have exactly 2 solutions? And the answer to that would be no. We already talked about on the concept summary the different options. 2 solutions was not an option. Okay? And here's the thing is if we have 2 linear equations, if you have 2 lines, the most they could intersect each other would be 1 time. Okay? It's not going to be magically that, you know, oh look, they intersected twice. Well, that's not a straight line, so that doesn't work. Okay? We will talk about at some point nonlinear, if we have a nonlinear equation. So for example, we're not doing this right now, but if you had a parabola and a linear equation, that could intersect at 2 points. Okay, that's for later though. Alright, so this gives you an idea of how to solve systems by graphing. Have a good day.